In a previous video, we discussed set operations on finite sets. Now we're going to talk about set operations that occur on infinite sets. So in example 1a and 1b, we're looking at the same sets. X is in a number such that it's less than or equal to 2, and x such that x is greater than 0. But we're looking at the union versus the intersection of the two. All right, so how does it work? Well, for the union, all we have to do is graph both sets. So how do we graph x being less than or equal to 2? Well, we start at 2, use a bracket because it's inclusive with the equal, and then we shade to the left forever because x is less than or equal to positive 2. So we have graphed the set of numbers x is less than or equal to 2. Let's now graph the set of numbers x is greater than 0. Well, if we look at 0, again, there's no equal here, so it's got to be a parenthesis. And that's at 0, like this. And now to graph that, we're just going to shade to the right because x is anything that's to the right of 0. It's greater than 0. Notice for the union, we're looking for x only has to belong in at least one of the sets of numbers, so that every number here is actually defined. And by that, we're saying that if you look at any number, let's take a look at, for example, a number that's down here somewhere. Maybe this is -9. Is -9 represented in a shaded part? Yes, it's represented in the reddish or the maroon type of shading. If we take any other value, let's say between the two, and let's call this actually 1, is 1 represented? Is it represented in either of the graphs, in either of the shaded regions? And it is. It's actually in both of them. And what about a number up here, let's say 5? 5 is actually represented as well. So any number, no matter where you put a dot, is in a shaded region. So what we say then for the union of the two would be the set of all real numbers. And as a graph, all you would do is just put 0 here, and then what I would do if it were me is just shade the entire graph, and I will shade it with a yellow one here, just left and right forever. Okay, so let me just go ahead and put it on the main graph itself. So let me erase what I have here. So the solution then would look like this. Okay, what about the intersection of the two? Well, where do they intersect? We saw that just a minute ago before I erased this. We're looking where they intersect each other. A good idea might be this, is to above or below, we have more room below, so let's put it below, is to graph each one of these independently, like this. And I'll put the 2 on here first, so there's 0, and here's 2. And then below that, let me put in what is it? Just 0 is what's listed. So if I were to graph this, it's less than or equal to 2. It's actually a bracket, so let's make this a bracket. And we would shade to the left of that, like this. And then for the other graph, it is greater than 0. So greater than 0 would be a parenthesis here, and then to the right. So if we stack these on top of each other, where will they intersect? Well, they're going to intersect between 0 and positive 2. So the graph then would look like this. We have a parenthesis on the 0 and a bracket on the 2, and then we simply shade in between like this. Now it's really important to understand why we're using a parenthesis and a bracket, a parenthesis on the 0, because if we look at 0, 0 is actually listed in the first set up here, but it is not because it's a parenthesis in the bottom set. So 0 does not belong in both sets, whereas 2 does belong on both. Why does it belong on the top one here? It's because it's a bracket, and because it's shaded, it's also listed in set, in the second set. So 2 is in both. So again, it has to be a parenthesis and a bracket. So let's go ahead and take a look at example number 2. In number 2, we have the sets x is less than -1. So we're talking about the union, first of all. That's very important. So let's talk about, or let's go ahead and graph that. It's less than -1, so it is no equal, so it'll be a parenthesis pointing to the left forever. As far as x is greater than or equal to +4, that's a bracket. And then it's greater than or equal to that, so it's shading to the right. So notice we have a parenthesis on the first set and then a bracket on the one on the right. Now, we have these both graphed up here. Look, do they intersect each other? No, they do not intersect each other. So what is the intersection of a set or two sets that do not intersect each other? Well, that's the empty set. So you would just leave, if it's a graph, you would just leave it blank. Or on the system, it probably gives you options for the empty set. Remember, the empty set could be the curly braces, and it could also be the symbol with an O through, with a line through it. All right, let's take a look at another example. We have a few more down here, it looks like. Looking at 3, we're looking for the union of -∞ to 2, inclusive of -2, that is. So it looks like this, and it is going to go forever to the left. So we're just going to make it like this with an arrow. And also for the union, it can be also from 4, which is another interval from 4 to infinity. So notice the use of parentheses versus brackets. They follow what we have here. So this is the union of these two sets. Now let's talk about the intersection of these two sets. We have -∞ all the way up to +4. So I'm going to just put this above the graph. So it's going to go like this. And it would be a bracket here at +4, and it goes to the left forever. To describe the second set, it would look like this, from -3 to infinity. So that's a parenthesis because it follows the parenthesis that's on this actual set, and it's greater than that. So the intersection of the two is between those two numbers. So it's between these two here. So the final graph then would be, put that in red, -3, like this. It is a parenthesis, and then it's a bracket up here at +4, and then we need to shade in between the two. So this is the graph of the two. Okay, again, that was the intersection of the two sets. All right, so let's scroll down here, see what we have for 5. Looks like 5a and 5b might be related to each other. And it is. We have the same two sets of numbers, same two intervals of numbers, and one is the union, the other is the intersection. So let's go ahead and graph the bracket 3 to infinity. So that would look like this. Bracket from 3 to infinity is here. And then for the second set, let's go ahead and put that in a light blue color, like this. It's from -1 to infinity. Now, remember, for the union, the sets of numbers only have to, or the elements, I should say, of the set of numbers only has to be in at least one of the sets. So actually, the blue one is the solution for the union of the two. So let's go ahead and erase both, and we'll just put in the actual solution. Before I do that, let me go ahead and do this. Where do these two overlap? They overlap here. So they overlap from +3 to infinity. So that's going to be the solution for the intersection. So let's go ahead and put that down here. We have the solution would be from +3, which is a bracket. It's in both sets, and to the right forever. So we'll go ahead now and erase and put the solution up here. For the or, it only has to be in one, at least one. So that is from -1. And that goes to infinity like this. And I actually made a little mistake here because the -1 is not inclusive of the either set. So this needs to be a parenthesis and not a bracket here. So let's put that in there like this. Don't forget, you can also check your ANS or your shaded region here and make sure that these values occur in at least or appear in at least one of the sets. So for example, -1 is not included because of the parenthesis, and it's not in either set up here as well. What about the number 0? Is it in either set? Yes, it actually appears in this first set. And so on and so forth. What about 3? 3 actually appears in both sets because it's shaded in either one, especially because of this bracket here. For the intersection, it has to be in both. So if we take a number like, let's say 5, is 5 in both values or in both intervals? Yes, 5 would be inside of this interval here, and 5 is also in this interval as well. So that's how you can check them. Let's look at one more example. We'll look at example 6. And this time the question is asked just a little differently. We have what's called the set builder notation, and it's describing two things. Notice the use of or. So x is less than or equal to -2, or x is greater than 5. So we have to account for both intervals on the union of the two, and that's what this is. So where is it less than or equal to -2? It's a bracket. Less than or equal to, we shade to the left. So we've defined the first set. Now what about the second? X is greater than 5. Greater has a parenthesis, and then we shade to the right. It's greater than 5. Now what about the interval notation? Notice there are two intervals that we have to talk about. Interval means there are, we're using the parentheses and the brackets. This time, because there are two intervals, we have to list them down here. So negative infinity up to positive, or that's a -2, and it's a bracket on the -2. Infinities always have parentheses. And notice the word or, we use the or symbol, which is the union symbol, I should say, and then now we now need to describe the interval for the second graphed area up here. So how do we say that? We start at 5, and it goes to the right forever. Looks like this. We follow the symbol. It cannot be 5, and it cannot be infinity, so we use parentheses. So just a different way to present the same kind of question, I guess. Similar questions, asked just slightly different. So anyway, I hope this helps you understand the set operations on sets.